In this video, we're going to talk about the cofactor expansion for determinants. Okay, so when a matrix A is 2 by 2, let's recall back in chapter 2 that when we first introduced the determinant, so if I have a matrix A with entries A, B, C, and D, this matrix is invertible. This matrix is invertible if and only if. So as we saw back in chapter 2, this is invertible if and only if A times D minus B times C is not equal to 0. So we need this condition that A times D minus B times C is not equal to 0 to guarantee that when we row reduce this matrix, it's going to have a pivot in each column and each row. Okay, so this expression AD minus BC, this is called the determinant of the matrix, the determinant of A. And the notation for that is sometimes we just write DET parentheses A. Okay, so then the natural question is, well, that's the determinant of a 2 by 2 matrix. What's the determinant if n is greater than 2? So what if I have more rows and more columns in my matrix? Okay, so let's let A be an n by n matrix. So I'm going to introduce some notation now, some terminology. So for 1 is less than or equal to I, comma, j is less than or equal to n. So I'll explain what this means, but let me go ahead and state something else first. So I'll come back and explain what this set of inequalities means. So when this is true, for 1 is less than or equal to I, comma, j, less than or equal to n, I'm going to let capital A subscript I, j be the n minus 1 by n minus 1 matrix that's formed by removing row I and column j from the matrix A. Okay, so before I do an example to explain, well, what is this exactly? What is this thing saying? I promise to explain these inequalities a little bit. So what this is saying is, so I sort of represents what row we're looking at in the matrix. J represents what column we're looking at. So collectively, I and j refer to some entry in the matrix. And this is basically saying that whatever row and whatever column I'm looking at, that row and column number has to be greater than or equal to 1. Like there's no row 0 or column 0 or negative numbers. And the biggest the row or column could be is n. That's why it's less than or equal to n. Okay, so let's do an example to get a feel for what this notation is saying. So let's say that A is this matrix right here. So let me give you guys 2 examples. So this was the case. Just to get a feel for it, what would capital A subscript 2 be? Well, what that means is, so here's the entry in row 2 and column 2. What I'm going to do is I'm going to remove that row, the second row in this case, and I'm going to move that column, so the second column. And then I'm going to write down the resulting matrix that I get. So the entries that are left over are, I have a 1, I have a 3, I have a 7, and a 9. So that's the matrix A sub 2, 2 that I get when I remove the second row and the second column from A. Okay, so let me go ahead and erase some of those lines and do one more example. Okay, so let's do one more of these. So let's say I wanted to know what A subscript 31 is, so A31. Well, then I look at the entry that's in row 3, column 1, that's the 7. I cross out this row, I eliminate this row, and I cross out its column. And what I'm left with is the matrix 2, 3, 5, 6. That's what A31 is. Okay, so again, I'm going to erase those lines I've just drawn. Those are there just to help me visualize what this resulting matrix is after I remove the rows and the columns. Okay, so I've gone ahead and erased those lines. Okay, so now I want to talk about a formula for the determinant when my matrix is 3 by 3. So if A is 3 by 3, so let's first write down what my matrix looks like in general. So 3 by 3 matrix A, so I'm going to say the very first entry, I'll just call it A sub 1, 1 to be general. And notice that when I use this lowercase a, that's talking about the entry. When I use a capital A like this, that's talking about a matrix when I remove like the corresponding row and the corresponding column. So A sub 1, 1 is this entry. The next entry in that row would be A sub 1, 2. So notice that the first digit here in the subscript, the 1, refers to the row. The second digit, the 2, refers to the column. So the next entry would be A1, 3 because it's row 1, column 3. The next row I would have A2, 1, A2, 2, and A2, 3. And the third row would be A3, 1, A3, 2, and A3, 3. Okay. So that said, I'm going to give a definition of what the determinant of this matrix is. Okay, so what the determinant is, so first what I do is, I look at A1, 1. And then I multiply that by the determinant of capital A1, 1. And we know how to figure that out now. I would sort of cross out the row this is in, and cross out the column this is in, and remove those. And the matrix that's left over, I find the determinant of that matrix. Okay, so let me erase those guidelines that I just drew. Okay, so then what I do is, so far I've looked at, I started with the first entry in this first row, the A1, 1. Then I go to the next entry in that first row, A1, 2. And it turns out what I do is I put a minus, and I write minus lowercase a, 1, 2. And then I multiply that by the determinant of capital A1, 2. So in other words, I would cross out the row that this entry is a part of, and the column this entry is a part of, and I would take the determinant of the resulting matrix. Okay, so let me go ahead and erase those lines that I just drew in. And so what I'm doing here with these coefficients is I'm starting to alternate their signs. Like A1, 1, I kept that how it was. But the A1, 2, I've alternated the sign. I've put a negative in front. Okay, so next, I take the next entry in that row, A1, 3, and I alternate the sign again. I switch it, so I would put plus A1, 3 times the determinant of capital A1, 3. So that would be crossing out the row that lowercase a1, 3 is in, and the column that it's in, and then looking at the resulting matrix. Okay, so if we expand this thing now, what do we get? Okay, so first I have lowercase a1, 1, and then when I take the determinant of capital A1, 1, I would cross out the row that entry is part of, and the column it's part of. And when I take the determinant of the resulting matrix, well, this is 2 by 2. And I know how to get the determinant of a 2 by 2 matrix. I sort of multiply these two elements. So A2, 2 minus A3, times A3, 3, and multiply them times A3, 3. And then I subtract that by the product of the other two elements in the opposite diagonal, minus A2, 3 times A3, 2. Okay, so now I got to do the same thing for the next term. So I have minus A1, 2 times this determinant. So for this determinant, okay, so let me go ahead and erase some of those lines I've drawn in. Okay, so for the determinant of this capital A1, 2, I would cross out the row that this entry is part of, and the column it's part of, and then I look at the resulting matrix, which is 2 by 2, and I find its determinant. So for its determinant, I would have to multiply these two entries together first, and then subtract that by multiplying these two entries. Okay, so doing that, first I multiply the A2, 1 times A3, 3, subtracted by A2, 3 times A3, 1. Okay. Alright, so next I have these green terms, so plus the A1, 3 times its corresponding determinant. So let's go ahead and erase those lines. So if we do the same thing for lowercase a1, 3, I cross out this row, I cross out its column, and with the matrix that I'm left with, I multiply these two elements minus the product of these two elements. So I get A2, 1 times A3, 2 minus A2, 2 times A3, 1. And that's my expression for this determinant. Okay, so let me go ahead and erase those lines one more time. So when we look at this formula that we have here, when we worked out what it was and got this whole thing, this is not that great in terms of how this looks. It's hard to memorize, but this earlier formula that we had in this step, that's very systematic. It's what's called a recursive formula. Like I defined the determinant of my 3x3 matrix, that definition involves these determinants of 2x2 matrices. So that's actually the next thing I want to note. A 3x3 determinant, my formula involved these 2x2 determinants. And it turns out that the general formula for even larger matrices follows this pattern. It follows this pattern that I started to write down here in this definition. Okay, so I really want to know this formula. This one is a whole lot easier to memorize. So let's generalize this now. Okay, so now let's talk about when A is n by n in general. So I want to give a definition of the determinant in this case. So if A is n by n, and n is greater than or equal to 2, then I'm going to define the determinant. That's why I've written this colon in front of the equal sign, because that means it's defined to be equal to. So the definition is, we're going to sort of expand it along that first row again. So I have the first entry in the first row times the determinant of the matrix when I remove that row and that column. So that's determinant of capital A11. And then I go to the next entry of the row, A12. I switch the sign, so I put a minus in front, times the determinant of the corresponding matrix, which is determinant of capital A12. So that's the matrix that I would get. That's the matrix that I would get if I remove row 1 and column 2. So this matrix, for example, is an n by 1 by n minus 1. Sorry, n minus 1 by n minus 1 matrix. Okay. But of course I don't stop there. The next term would be, I alternate the sign again, I add up a plus. And I keep going until I get to the last term. And with the last term, we know we're going to have an A1n. But in front of that, I'm not totally sure whether we're going to have a minus or a plus. But what it will be is it's going to follow the same pattern. It's going to be negative 1 to a power, negative 1 to the 1 plus n power. Okay, so depending on what n is, that'll tell me whether this will end up being positive or end up being negative. Okay, and then I still have to multiply this by the determinant of capital A1n. Okay, so that's the formula for the determinant. That's the definition of it. So let me talk about some notation. It's really common to write the determinant of A as, we put A inside of these absolute value bars. And it's clear from the context in problems that we're not talking about just the absolute value of a number, because the thing inside of it is a matrix. Okay, so when we see this absolute value looking notation, that means determinant. Okay, so before I do an example computing the determinant using this formula, I want to state a key theorem, which is, it turns out that I can compute the determinant using these alternating sums that I have here, where I'm switching minus, plus, using any row or column. Because in this definition up here, we just took the entries like A11, A12, all the way up to A1n of the first row. But it turns out we could do it in any row or any column and it always get the same number. And that, I think, is very remarkable. But let me first tell you guys what this pattern is. So this pattern is what I use to determine, well, what are the signs that I'm going to use depending on my row and column. So the pattern is, I always start with a plus. Like the very first entry in this very first row and column is always considered a plus. That's why there's no negative sign written in front of the A11. And then I start alternating from there. So next to it, I'd have a minus and then a plus, and I would keep going like this. Underneath this plus, I'd have a minus, and then it alternates, plus, minus, keeps going. Underneath that, I would alternate, so plus, keep going. And it would keep going down, and then all the way across. Okay, let's do an example. Let's practice using this. Okay, so let's compute the determinant of this matrix. So the first row is 2, 3, 5. The next row is 0, 3, 7. The last row is 0, 0, 5. By using this expansion, so this expansion is what's called a cofactor expansion, along the second row. So what does that look like? So if I expand along the second row, let's write out what the determinant is. The determinant, so what I begin by doing is, I take the first element of that row, which is a 0. And then I have to figure out the sign that is associated with it. Well, the signs are going to be, I always start with the positive here. Actually, let me just draw another corresponding matrix so I don't clutter this. I have a 3 by 3 matrix, and the signs of that would be plus, minus, plus, minus, plus, minus, plus, minus, plus. So where this 0 is corresponds to a negative sign. So I have to put a negative in front of the 0. And then what I do is I multiply it by the determinant, so I'm using this absolute value sort of notation for the determinant of the matrix that I get when I cross out the row that 0 is in and the column it's in. So that's, I have 3, a 5, and I have a 0 and a 5. Okay, so I have to continue along this second row. So the next entry of that second row is this 3. Okay, so I'd write the 3. And what's the sign associated with the 3? Well, the sign associated with that 3 is this, this positive. Okay, so I put a plus in front of the 3. And then I multiply it by a determinant. So the determinant I get when I cross out the row the 3 is a part of, and the column it's part of. So that leaves me with 2, 5, 0, 5. Okay, so let's erase those extra lines that I drew in. And then finally we go to the last entry of that row, which is a 7. So I'll write 7. 7. And then the sign associated with the 7 is this negative symbol. Okay, and then I multiply that by its corresponding determinant that I get when I cross out the row the 7 is a part of and the column the 7 is a part of. So that leaves me with the entries 2, 3, 0, 0. Okay, so let's work out this. Because at this point I know how to compute 2 by 2 determinants. They're easy. Okay, well, with this first term I have 0 times something, which is clearly 0. With the next determinant, well, I have the 3 in front. And then to work out what this 2 by 2 determinant is, I multiply these two terms, which gives me 10, minus what I get when I multiply these two terms, which is 0. Okay, and then I have this minus 7 times this last determinant. So I multiply the 2 times the 0, which is 0, minus what I get when I multiply the 3 times the 0, which is also 0. Okay, so what I'm left with is, I have 0 plus 30 minus 0, which is just 30. And that is my determinant. So it'll turn out that knowing this determinant, the fact that this is 30, the fact that this is not 0, will tell me that my matrix is not invertible. And we'll see why in the next video. Okay, so that's a little bit of a preview of the next video. But let's talk about how we can compute this determinant in another way. So in part B, I want to use a cofactor expansion, but this time along any row or column. So I have a choice, but I want to do it in a way that minimizes the number of computations I have to do. Okay, so if I could choose any row or column to expand this along, one thing I noticed from the computation I did above, it's really nice when we have a 0 as our entry, because then this whole term goes away. So let's pick either a row or a column that has the most number of zeros. So for example, column 1 would be a good choice. Row 3 would also have been a good choice. But if we expand along column 1, the first column, and the reason why I'm doing that is there's lots of zeros in there. Lots of zeros. What would we get? So determinant of A would be equal to, so the first entry in that column is this 2. And the sign associated to the 2, that's positive, because the very first entry here, we think of that as there being a positive there. Okay, times its corresponding determinant. So if I remove the row and the column the 2 is a part of, let's do this more quickly this time. We are left with 3, 7, 0, 5. Then I go to the next entry in that column, which is 0. And I switch the sign, so I put a minus in front. And then it's going to be 0 times whatever its determinant is, but that doesn't matter, because when I multiply by 0, it's going to be 0. Okay, and then I go to the next entry of that column, which is 0 again. And then I switch the sign, so minus to a plus, times its corresponding determinant. But that's not going to matter either, because 0 times whatever is going to be 0. So what I'm left with is 2 times this first determinant. So I'll multiply the 3 times the 5, which gives me 15, minus 7 times the 0, which gives me 0. And then these other two terms, so I'll have a minus 0, and then a plus 0. So I'm left with 2 times 15, which is 30. And notice that that is the same as the answer that we got above when we expanded it along the second row. And that, I think, is pretty remarkable. It's not immediately obvious at all why doing this cofactor expansion along different rows or columns should give us the same value. So the proof of this is actually really, really long and tedious, so I'm not going to do that. Instead, I want to prioritize understanding how to do this computation.